What problem does the proposed URIAL prompt strategy aim to address in large language models, LLMs?
The proposed URIAL prompt strategy aims to address the issue of large language models, LLMs, struggling to follow instructions directly from prompts. It aims to improve the alignment of base models without the need for extensive fine-tuning by leveraging in-context learning, ICL. The goal is to enable base models to interact with users and follow instructions at a similar level to instruction fine-tuned models by including carefully selected question-answer pairs in the prompt. URIAL seeks to customize base models through ICL without changing weights, offering a simpler and more flexible approach to alignment. The strategy is evaluated across various base models, including GPT-4 base, on instruction following benchmarks like MT-Bench and AlpacaVal 2.0. While URIAL achieves reasonable performance, it still lags behind instruction fine-tuned models, prompting the exploration of strategies to enhance URIAL, such as incorporating many-shot in-context learning and optimizing the selection of in-context examples to improve instruction following ability.
How does the proposed URIAL prompt strategy work, and how is it different from traditional alignment methods, such as supervised fine-tuning, SFT, and reinforcement learning, RLHF?
The proposed URIAL prompt strategy works by incorporating in-context learning, ICL, into large language models, LLMs, through the inclusion of carefully selected question-answer pairs in the prompt. This strategy allows base models to follow instructions and interact with users at a similar level to instruction fine-tuned models, without the need for changing model weights. URIAL aims to improve instruction following ability by optimizing the selection of in-context examples to enhance model performance on tasks like MT-Bench and AlpacaVal 2.0. URIAL differs from traditional alignment methods like supervised fine-tuning, SFT, and reinforcement learning, RLHF, in that it leverages ICL to guide the model's behavior without directly adjusting model parameters. While SFT relies on fine-tuning the model on instruction datasets, and RLHF uses reinforcement learning to train the model, URIAL focuses on providing in-context examples to enhance the model's ability to follow instructions. Additionally, URIAL's approach of selecting and incorporating a small number of high-quality demonstrations into the prompt contrasts with the many-shot ICL approach used in tasks like summarization, translation, or classification, where providing numerous examples is more beneficial. Overall, URIAL offers a simpler and more flexible way to customize base models for instruction-following tasks compared to traditional alignment methods.
What are the main findings when comparing the performance of base models with the URIAL prompt to their instruction fine-tuned versions on benchmarks like MT-Bench and AlpacaVal 2.0?
The main findings when comparing the performance of base models with the URIAL prompt to their instruction fine-tuned versions on benchmarks like MT-Bench and AlpacaVal 2.0 are as follows. 1. Base models with the URIAL prompt achieve competitive performance on the first-turn score, but generally cannot match the performance of their instruction fine-tuned counterparts, except for Llama 2-7b and Mistral 7b v0. 1-2. The second-turn score with the URIAL prompt is notably worse than for instruction-tuned LLMs, likely due to the lack of multi-turn demonstrations in the context. 3. Providing questions with correct answers is crucial for the effectiveness of in-context learning, ICL, on instruction-following tasks, while adding incorrect demonstrations can degrade model performance. 4. The study focuses on the first-turn score and single-round conversations, leaving the extension of ICL for multi-round conversations to future work. 5. The results suggest that while the URIAL prompt strategy shows reasonable performance, it still lags behind instruction fine-tuned models, prompting the exploration of strategies to enhance URIAL, such as leveraging models with extensive context windows and many-shot ICL approaches. 6. The findings highlight the nuanced nature of ICL as an alignment technique and emphasize the importance of question-answer matching for in-context demonstrations in achieving successful instruction following performance. 7. The study also indicates that a greedy search approach can help bridge the performance gap between base models with the URIAL prompt and fine-tuned models, showcasing the potential of optimizing ICL prompts for improved results. 8. The transferability of in-context examples across different base LLMs varies, suggesting that the effectiveness of ICL demonstrations may depend on the specific characteristics and pre-training of each model.
How is the effectiveness of in-context learning, ICL, for instruction following tasks evaluated in the paper, particularly in terms of the number and selection of in-context examples used?
The effectiveness of in-context learning, ICL, for instruction following tasks is evaluated in the paper by testing various strategies to improve the URIAL prompt strategy proposed by the authors. The paper explores the impact of different numbers and selection criteria of in-context examples on the performance of base models. Initially, the study examines the addition of high-quality demonstrations from existing instruction datasets to the URIAL prompt, which only leads to limited improvements compared to URIAL. A simple greedy algorithm is then proposed to select in-context examples that optimize the MT bench score, nearly closing the performance gap between Mistral 7B VO2 and Mistral 7B Instruct VO2 by adding 2 additional demonstrations to the URIAL prompt. The paper also investigates the importance of question-answer matching for in-context demonstrations, showing that using correct answers is crucial for the success of ICL in instruction-following tasks. Furthermore, the transferability of in-context examples across different base models is analyzed, indicating that the effectiveness of ICL demonstrations may vary depending on the specific characteristics of each model. Overall, the paper systematically evaluates the impact of the number and selection of in-context examples on the performance of base models in instruction-following tasks, highlighting the significance of careful curation and matching of question-answer pairs for successful ICL implementation.
What are the key takeaways regarding the importance of question-answer matching for in-context demonstrations in the context of instruction-following tasks, as discussed in the paper?
The key takeaway regarding the importance of question-answer matching for in-context demonstrations in the context of instruction-following tasks, as discussed in the paper, is that using correct answers with both correct content and style is crucial for the success of in-context learning, ICL, for instruction following. The paper shows that providing questions without answers surprisingly leads to good results, while permuting answers with questions significantly degrades performance. Additionally, sampling answers from in-domain categories, where the content may be incorrect but the style remains appropriate, still achieves relatively good scores. However, sampling answers from out-of-domain categories, where both content and style are incorrect, results in the worst instruction-following performance. The study demonstrates that the effectiveness of ICL for instruction following heavily relies on matching questions with correct answers, especially as the number of examples increases. This finding suggests that ICL for instruction following differs from other tasks and highlights the critical role of question-answer matching in optimizing performance in this context.
Based on the results presented, how transferable are the in-context examples found by the greedy search to different base LLMs like Llama 2 to 7B 80K and Mixtrol-8 by 22B V0.1 to 4-bit?
The in-context examples found by the greedy search show mixed transferability to different base LLMs like Llama 2 to 7B 80K and Mixtrol-8 by 22B V0.1 to 4-bit. When applied to Llama 2 to 7B 80K, the new examples can increase the MT bench score by plus 0.47, indicating some level of transferability. However, when applied to Mixtrol-8 by 22B V0.1 to 4-bit, the results are not consistent, with some cases showing worse performance than the original URIAL. This suggests that the effectiveness of the in-context examples may vary across different base LLMs, potentially due to differences in their pre-training. The analysis implies that while the in-context examples found by the greedy search can have a positive impact on certain models, their transferability to all base LLMs may not be guaranteed, highlighting the importance of considering model-specific characteristics when utilizing in-context examples for alignment purposes.